All right, good afternoon, everybody. My name is Puseletso Diketane, and I am an APC engineer here at Foresight. Thank you very much again for taking time out of your busy schedules to be able to join us in this webinar, where we will be looking at the application of APC within the flotation space. So joining me was supposed to be Evan Jacobs, but unfortunately, he will not be able to make this webinar. So please do accept our apologies on that end. However, I do assure you, we will still be able to have a fruitful session together in the short time that we have together. And you should be able to see Evan Jacobs in the upcoming webinars that we will be hosting as the APC team. All right, let's get into the webinar. So just a brief overview of the topics that we will be covering today. Firstly, we will be looking at an introduction into flotation as a process. Then we will have an overview of your APC system. Then we'll dive into the challenges that we often see in the flotation space in terms of control and all the solutions that the APC system allows us to implement to be able to solve these challenges. We will also look at the process requirements in terms of ensuring that the APC system operates efficiently. And we will close off the webinar by looking at a couple of the case studies that we had internally in the Foresight company, where we implemented the APC system at our client site and what the benefits were for those clients. All right, taking a quick overview of flotation. Essentially, the process of froth flotation is a process in which we have our finely milled material that is being fed into your flotation cells as a slurry. Now, to this slurry, you also have air that is passed through it to generate bubbles within your flotation cell, onto which your valuable minerals will be able to attach themselves. Now, what we also see in the flotation cells is that we have reagents such as our collectors, our frothers, and our depressants that are being added in our flotation cells and responsible for ensuring that the valuable minerals become hydrophobic. So once the valuable material is hydrophobic, it will then be able to attach themselves, or rather attach themselves to the bubbles that we created within our flotation cells, and will rise to the top of the flotation cells to form this mineral-rich and stable froth. Now, all the invaluable materials that we have still remaining within our flotation circuit will stay in the pulp of our flotation cells and be sent downstream to your tailings section, where you will be recovering more of your invaluable material. Now, whilst the tailings streams are being processed in your downstream processes for processing tailings streams, in each flotation cell, we have collection of your froth, which that is then sent to your concentration processes downstream, so we can further concentrate our final product and be able to get it in the right state so that the plant can be able to sell it. Now, in industrial flotation processes, it is actually necessary for a complex configuration of multiple of these flotation cells to be used so that we can actually recover a large amount of our valuable materials that is being fed into the plant. Now, this collection of cells is actually referred to as a bank of cells, while the collection of these banks is referred to as a train of cells. Now, the different banks of cells that we find in the froth flotation space firstly includes your roughers, where we see the highest recovery of your valuable material. We then have your cleaners, where we see about a moderate recovery of our valuable materials. And lastly, we have our scavengers, which is the final stage of recovering the smallest amounts of valuable material that can still be present in the process before we send our material to the waste section. Now, the tails streams from one of the flotation cells, or rather all the flotation cells, is actually typically used as the feed stream to the next flotation cell that comes afterward. And because of this, it's actually why we refer to the collection of cells within a flotation circuit as a train of flotation cells. Now, the concentrate product from this train of flotation cells is typically fed to another train of flotation cells to further clean our product and ensure that we get our final product in the quality and the grade that we rather want for in terms of recovery materials within the process. All right, so now that we have covered flotation, let's now have a quick look at what the APC system is and how we can implement it in the flotation space later on. So in simple terms, the APC system is an advanced tool that actually aims to empower plants to continuously maintain stability within their processes and be able to push their process to the most optimum economically viable region. Now, the benefits that we often see through the implementation of the APC in a process often includes things such as seeing an increase in your production, a reduction in the amount of energy that you use in your process, and being able to efficiently mitigate any process upsets, and last but not least, being able to reduce the variability within your final product. All right. Now, one may ask themselves, and a simple question to say, how is the APC system different from the traditional control that we see most of our processes applying? Now, in traditional control, what we see is that the operator is the one that is solely responsible for setting the set point of the flotation circuit, which then means that they are the ones that are responsible for determining where the process should be operating. What we also see is that the operator is the one that is responsible for mitigating any process upsets from any disturbances that can enter the circuit or when a safety interlock system has been triggered. Now, this is more of a reactive approach in terms of control, where the process first needs to be destabilized and then needs to be restabilized through the operator's intervention. So the advantage that we have through utilizing the APC system is that the APC takes more of a proactive approach towards control. So the APC system actually reads in the limits and targets that the operator and the process engineer have set for the plant, and then it then uses this information to calculate all the necessary changes it needs to make in your manipulated variables to be able to achieve the desired output from your process, while continuously making sure at all times that we adhere to the operator's limits and do not trigger any safety interlock systems that have been put in place within your process. Now, through this measure, the APC is actually able to ensure that we are able to continuously maintain stability within our process so that we can have more time to actually push the process towards its economically beneficial region and not focus most of our energies towards pushing the process towards, or rather prioritizing stability within our process. All right, now that we have covered the background on flotation and APC, let's have a look at the control challenges that we typically encounter in the froth flotation space. So the first challenge that we will discuss is that of process dynamics within your flotation circuit. Now, since flotation cells contain many individual cells, the interaction between these cells can be quite complex. And because of that, what we see is that there's very long delays between a process change that is being made at the front end of your process and the effect of it being actually seen at the back end of your process. Furthermore, within your flotation cells, we see that they are highly interactive in their nature since they are operated in series. So what we see is that any changes that you have in one of your cells within your flotation train will actually affect the operating parameters of all of the other flotation cells downstream from where you implemented the change. Now, another challenge that we have with regards to the dynamics in the flotation circuit that we often see in our processes is relative to the large amounts of materials that we are processing within our flotation circuit when we already have large volumes in terms of physical capacity of your flotation cells. Now, this then actually means that it actually takes quite a long time for your effects that are being made in one of the flotation cells to pass through your system and be able to reach restabilization again. So this actually means that if one of your flotation cells is being disturbed, you will have quite a long time in terms of restabilizing your flotation circuit because the disturbance still has to pass through all the different flotation cells. All right, still on the topic of dynamics, another challenge we experience is in the flotation space is in the differences in the time delays on terms of the cell's responses. So for example, if a change is made in the reagent dosing of your first cell in your flotation train, the effect of that concentrate grade will actually be seen quite quickly because the point at which you measure your concentrate grade and the point at which you introduce your reagent dosing and the distance between those 2 points is relatively short. But what we also see is that it will take quite a very long time to see the effect in terms of your tails grade measurement at the end of your flotation train. And that's largely because the point where we measure our tails grade in our flotation circuit is relatively far from the point that where we introduced our reagent dosing. Now, since the calculated mineral recovery is actually very sensitive to the tails grade, so it is actually important for the control systems that are implemented on these circuits to be aware of these delays in terms of your input and output responses of your circuit. All right, now the second challenge that we see within the froth flotation space is the presence of collinearities between your cells. So as I mentioned earlier, the main control inputs for your flotation circuit are namely your air addition into your flotation cells, the amount of material that you have in your flotation cells, which is typically measured by your pulp level. And lastly, the amount of reagents that you are dosing within your flotation circuit. Now, these three inputs actually have a correlated effect on the process output. That means it actually affects how much of your valuable materials you're able to recover and how much of your unwanted material is actually captured in this stream. So as a result, it is important to understand the best way to manipulate these three inputs in order to achieve the specified control objective for your flotation circuit. Now, in an instance where we have an incorrect control strategy that is being used for your process, it could actually lead to the control system working against itself because you have the controller now needing to move to be able to correct the control actions it has made in one of your inputs. So this is actually an unideal state of operating your control system because the controller continuously works to correct its own measures instead of focusing its powers in optimizing the process, which is the fundamental reason of why we have an advanced control system on our processes. All right, just to take a quick, have a look at a quick example of collinearities within your process. We will see in the image on the screen where we have our inputs of the two adjacent flotation cells being very similar, but not having the same or rather identical effect on the controlled variable. So in this case, then we would have a question being raised as to how is the control system supposed to decide on which inputs to which cell is it supposed to move in order to achieve the control objective that we have set for our system. Now, how we deal with this particular matter in many cases, the easiest way essentially is to configure a control system to consider inputs that are similar to each other to actually have the same effect on the output, which will cause the control system to use each input equally to achieve the control objective that we have set for our flotation process. Now, what we also see within the flotation space is that the response in terms of inputs or rather outputs of your first flotation cell and your last flotation cells is quite different to each other. So because of that differences, we don't need to implement this strategy. We can actually just allow the control system to utilize these differences and independently move the inputs to your flotation cells to accurately be able to achieve the control objective that we have set for your flotation circuit. All right, so the next challenge we see in flotation is the maintenance of manipulated variable profiles. So since the tails of one flotation cell is used as a feed to the next flotation cell, the amount of valuable mineral within the cells actually decreases as we move down your train of flotation cells. So it is therefore important to maintain a profile of the manipulated variable throughout the train of your cells to ensure that the NV values are appropriate appropriate for the concentration of the valuable material. Now, in traditional operations on our plants, what we typically see is that this profile is actually the responsibility of the operator to maintain it. But what we also often experience is that this particular measure can be overlooked at times, which then leads to excessive recovery of your waste material within your final product streams, which is essentially not what we are aiming for within our operations in the flotation space, because you want to continuously maintain the right quality of your final product and have all of your waste materials reporting to the waste section. All right, so the final challenge that we will look at is the challenge of having intermittent measurements within your flotation circuit. Now, the minerals processing environment is actually quite a harsh environment. And although the equipment that we use in this space is equipment that is built to be able to handle these harsh conditions, what we typically see with our client is that they constantly have this reality of dealing with blockages within their instrumentations or having any other faults with regards to the instrumentations that are used within the flotation circuit. Now, if the intermittent measurements that we read from these instrumentations are actually incorrect or not correctly handled in an online control system, it can actually lead to instances where your control system will have drastic control actions that are being implemented as a result to the faulty measurements that we are reading in. And that's not an instance that we want to be in, because we find that the controller now is continuously responding to any faults in mechanical faults of the instrumentation and not seeing the actual effect, or rather the actual performance of the process. So it's responding more to the issue that we have in terms of the instrumentation, and as opposed to actually having a response to the actual operations of your flotation circuit. All right, now that we have discussed the challenges we have in flotation, let's have a quick look at how we can harness the power of the APC to resolve these issues that we have in the flotation space in terms of control. All right, so taking a look at the first problem, which is the problem of having complicated dynamics within your flotation process, let's see how the APC system can be able to help us in resolving this particular issue. So the APC that we use here at Foresight is a model-based APC, which is actually able to capture the complex steady state and dynamic calculations within your process in the models it generates between each of the flotation cells in the circuit and their associated responses, or rather associated impacts on the controlled variables. So now this set of relationships is actually solved in the online controller at each of the controller's execution cycles in order to achieve the control and optimization objectives that we have for our process. Now, this particular technique actually allows for the time delays, your time steady states, your steady state gains, and more of your control parameters of each of the flotation cells to be modeled individually in terms of your operations and control operations of your process. And this will ensure that we appropriately account for them within the controller in terms of making decisions on how best we can achieve the control objectives that have been set out for your flotation circuit. So in terms of resolving collinearity within the process, the APC that we have here at Foresight actually allows for us to do what we call a collinearity repair onto our flotation cells, in which the individual models are rotated slightly to make them perfectly collinear. This will then make them identical from the controller's perspective and actually allow the controller to move them identical to each other when the controller is online and controlling the plant. Now, this is quite a useful tool to be able to apply, especially for flotation cells that are adjacent to each other and that have the same impact on your output. So we want to ensure that we can use them identically so that we can just have the relative same impact on our final output in the process. Alternatively, what we also have as a feature within the foresight APC to resolve collinearity is to actually remove the collinearity within your process completely through what we call a feature that we call called or rotation, which means that the models will be quite different from each other from the controller perspective, and we will be able to move the variables that are involved in the controller independent of each other. Now, this particular feature is important for features or rather flotation cells that are far away from each other and have different impacts on our final product or rather on our process, so that we can actually use them or harness the differences between them to effectively control your final product and be able to effectively achieve the control objective that has been set for your process. All right, now maintaining profiles down a flotation train is quite straightforward in the foresight APC through the usage of custom calculations in the controller. Now, this allows for new controlled variables to actually be defined, which represent the desired profile limits. So the controller can actually be tuned to obey these limits, which will then create the desired MV profile down your flotation train. Now, this actually ensures that the correct MVs are maintained in the correct level throughout your flotation train, which actually helps in maintaining the process in its linear operating region. All right, now data validation is the final and possibly the most important challenge that we need to overcome in your flotation processes. So the foresight APC that we implement on our client site actually allows for data to be read in from the plant and be validated first before a control action is executed on that measurement. Now, this actually ensures that the controller does not respond to any inaccurate raw data from the plant, which is actually prone to measures such as drifting, having noise spikes in them, and freezing. Now, in an instance when we have a faulty measurement that is detected, the APC will be able to leverage from the dynamic process models to temporarily estimate the missing data until the measurement that we are receiving from the plant is deemed as good for control and usage within the APC. So through implementing this, the APC actually allows for an instance where we can operate it uninterruptedly and ensure that we can harness the powers of the APC. We can continuously harness the powers of the APC and be able to push the process towards its more economically viable region and rather focus on that instead of continuously focusing on trying to restabilize the process. All right, now that we have seen how APC can empower flotation circuits to be able to resolve their control issues, it is actually important to discuss some of the key requirements of the APC system to operate efficiently. Now, to derive the best performance by the APC system, it is important to ensure that the process instrumentation that you are using within your flotation space and the APC depends on them is actually well calibrated and do not have any faults in terms of their operation. So firstly, it is important to ensure that all the control valves that are involved in terms of your air addition lines into your flotation cells, your cell tails valves, and all the other valves that are involved in your flotation circuit are all well calibrated and can track the set points that the APC is setting. Now, if we have any incorrect performances by these valves, we will unfortunately have poor control of our product flow and our product grade, which is not what we want to be, not the state we want to be in, because fundamentally operating a process, you want to be able to accurately control your product flow and grade so that you can have better financial benefits for your process. So it's also important to ensure that all flow meters that are used within your process are well calibrated so that we can get accurate measurements from them to be able to accurately read your product flow, your reagent dosaging, your feed flow, and your air addition within your flotation cells. If we ever have an instance where we have incorrect values that are being read in these devices, it will actually result in inaccurate mitigations to any disturbances that can happen in your circuit, and actually affect the quality of your final product, because we can't actually accurately measure how much of material we're processing and how much we are dosing and how much of our final product we are producing and at what quality or rather grade. So the level sensors also have to be accurately calibrated so that the APC can have clear view of how much materials is available within your flotation cells, so it can accurately control the flow of your final product. We also need to ensure that we have well-performing grade analyzers so that we can ensure that the APC is aware that it is producing the right quality of your final product. Now, in a process where we have froth velocity cameras that are available, it is important to ensure that these are also well calibrated, so we are able to track, or rather accurately track, the amount of valuable materials that we are deriving from our flotation cells, which will be able to see as to how much of our materials we're sending into your concentration section of your final product. All right, so as I explained, to wrap up the webinar, we will be looking at 2 case studies where we implemented the APC and the benefits that these particular clients were able to realize through the implementation of the APC system. Now, the first client that we will be looking at is a copper flotation plant that is owned by First Quantum, where they were fundamentally facing the challenge of cell interactions within the flotation circuit, which was inherently causing a lot of instabilities within their process. Now, they were also facing challenges with maintaining their product grade within spec, which then resulted in them not accurately being able to control their recovery of their process. So through the implementation of the APC and applying the solutions that we discussed earlier of decoupling the flotation cells and accurately capturing the dynamics of the process, the client was actually to see that through the implementation of the APC, they were able to get an approximately 3% improvement in their concentrate grade and about a 5% increase in their total copper recovery. Now, as you can see from these numbers, it actually proves that through the implementation of the APC, this particular client, which is First Quantum, was actually able to produce more copper in their process at a much higher and steadier grade. All right, so the next case study that we will be looking at is a lead zinc flotation process that is owned by Glencore in Mount Isa, Australia. So similar to First Quantum, what they were also having challenges with is the interactive nature of their flotation cells. Now, additionally to this challenge, they were also experiencing a challenge of having high variabilities in their feed in terms of their feed grade and feed flow rate, which made manual control actually manual control, which is what they were using before we implemented the APC system, quite difficult in terms of stabilizing their process and being able to optimize their process. So an APC system for this particular client was fitted on their rougher section, their recleaners, and their scavenger circuits to be able to optimize their final concentrate grade. So for this particular client, what we saw was through the implementation of the APC, Glencore was actually able to see a 1.35% increase in their recovery at a mean feed grade, and overall 49% reduction in the variability within the concentrate grade, and an overall $2 million increase in their revenue per year. Now, this actually proves that through stabilizing the flotation circuit through the implementation of the APC actually allows our plants to see a positive economical operations of their process. All right, and that is all from me, everybody, in the short time that we had together. I hope you found these sessions very valuable. But before I release you, I would like to bring your attention to the upcoming webinars that we will be having as the APC team here at Foresight. On the 5th of November, you will be invited to a webinar where myself and my colleague Johan de Bruin will be taking you through the implementation of APC within the milling space. And on the 19th of November, you will have Johan de Bruin joined by Ewan Jacobs, as promised, discussing the application of APC within the crushing industry. Otherwise, on my side, everybody, thank you very much again for taking time to join us in this short webinar where we looked at the application of the APC in the flotation space. And I am looking forward to having you join us again on the 5th of November, where we will be looking at APC in the milling space. All right. Thank you, everybody. Hope you have a good afternoon and take care.